All right. So let's continue our discussion. On Monge Ampere. This is the bigger topic. So we already discussed the notion of Alexandrov solution. And let me just tell you that Alexandrov had introduced this notion to solve the prescribed Gaussian curvature problem. So which is to give me so you have a convex set, and at every point you have the Gaussian curvature. So this is the Minkowski's problem. So the thing is that there are a bunch of quantities that I simply don't have time to define. So if I know any convex set, I know that I can parameterize it by Sn-1. It's topologically Sn-1. Okay. So there you have the Gauss map. Okay. So what you do is that for any convex set, you have to sort of top up the Gauss map, which is to say that at every point, like the coordinate over here, you have to take all supporting planes and the normals to that. Okay. And these belong to Sn-1, and then you take the measure of that. Okay. Hn-1 measure of that is Sn-1. And then the prescribed Gaussian curvature problem is that GK, that Gaussian curvature measure, should be equal to some Borel measure. Okay, so that is the prescribed Gaussian curvature problem, and then you prescribe a smooth density. Now, let me tell you that you may have learned the Gauss-Bonnet theorem, right? So there are restrictions that comes in. There are topological restrictions that comes in. That integral of the Gaussian curvature has to be equal to the 2 by the Euler characteristic, right? That we know. So of course, I mean, for a convex set, I know that topologically it is Sn-1, so that takes care of it. But then for the measure that you need, the minimal condition that you need, which sort of reflects, which also takes into account such a topological sort of restriction, is that the corresponding Borel measure that you want to solve this Minkowski problem for, mu of Sn-1 should be equal to, so the Gaussian curvature, so the problem is finding K such that the Gaussian curvature measure is equal to mu, and this mu has to have this topological restriction that mu of this Sn-1 has to be equal to the measure of Sn-1. Okay, so this is minimally the restrictions that you have to put on this page. Okay, so this is one thing that is there with you. So Alexandrov found, and there is also the another thing where you have to define the polar set corresponding to this and that. So what Alexandrov did was that he devised this theory that I described to solve this Minkowski's problem by this Perron's method. Okay, and then he found necessary and sufficient conditions on the measures so that this problem can be solved. So there are a bunch of quantities. So the Minkowski's problem is that at every point you have this Gaussian curvature measure. Okay, and then the Gauss curvature is just the density of that. Okay. The Gaussian curvature is just the density of that measure. Okay, so you want to find a case so that at every point the Gaussian curvature is GK of x. So once you solve the Alexandrov problems, okay, so then this is also one such problem where the Cafarelli's theory applies. Okay, in some sense. But for that, I need to tell you that. So this is one problem where eventually the Cafarelli's theory will apply. But at this point, I will skip this motivation because we just look at this at the very end because of the time constraints that we have. Otherwise, ideally, we could get into some discussion. And then at a later point, we could have come back. But that will be a waste of time given the brevity of the time that we have. Okay, so this is it. So this is one thing, but the Cafarelli's theory will eventually apply. So, and what Debocrates said is that you cannot have a surface, roughly he said, that which has a line and then which becomes like this. Because minimally it's like the Monge Ampere equals to this, because any convex set can be represented as a Lipschitz graph. So if I have that this GK is smooth enough, you will have that in the Monge Ampere sense, this is equal to some f of x. And if there is a line, okay, and at these points you can cut a section, okay. So of course you cannot cut a section here, you cannot normalize it here, but if you follow this, you get an extremal point where you can cut a section, okay, that is described. And at this section, you will have that a good theory can be done. So I will now describe this matter, maybe now or later you will see. And once you do that, so what it tells you is that, so this is the generalized notion of strict convexity, which is that at a point, you can cut a section so that this section is compactly contained in this ground region omega, okay, where you sort of parameterize the problem. And once you cut a section, at one scale it is strictly convex, then the strictly convex, so then below that, the strict convexity has a uniform character, has a universal sort of character. That is, this cannot be any flat, this has to curve. And so therefore, you cannot have a flat piece, okay? Because essentially over here, the key thing that helps you is that this whole surface has to round up, okay? So now, however, this does not generally happen in local situation, but this is enforced by this global condition that this is the boundary of a convex set, this K that you find as a solution. And this solution is found by variation of the Perron method, and a lot of other ingredients are required. Okay, so a reasonable description of that you can find in the book of Figali on Monge Ampere, but it might not have all the details, and that refers to other references that you can sort of trace if you're interested. So existence is one thing, okay, but the regularity was an issue that was handled much later, and that follows from the Cafarelli's theory. Not in two dimensions, but otherwise, okay, like for two surfaces in R3, the theory is classical. So therefore, this takes us to this question of singular solution. So singular solutions means where the string convexity degenerates. So string convexity, the way I was trying to allude to is more like you can cut a section, but then it translates to the strict convexity in the conventional sense for all the region that is below. Okay, and
yeah, how do you export this possibility by this constraint that?
So the thing is that if there is a line, you follow this line till you hit this point,
right.
And at this point, since you are cutting a section, so this is convex. So in the bigger domain, this section that you have, which is over here, is compactly contained in the region, so you don't see the boundary values. And there you normalize the section by whatever I would say in a while. There you would have that the solution is strictly convex, okay, and therefore it is C2 alpha, C4 alpha, depending on this. So therefore it cannot contain a line. So if you have a flat piece, you follow that point till you hit the first extremal point. And wherever you do, and extremal points are those where you can slice it by plane so that there is a section below, which is the characterization of extremal point. But then if you can slice a section below so that you can start the process, you will have a section which is compactly contained, and then that will exclude the, you know that all the way up to here, there is a fine line joining this point to this point, and that cannot be because of strict convexity, so this has to curve up. Okay, so this line gets, so therefore this flat piece in principle doesn't even exist. Likewise, you may say that, okay, you've left this chunk, then you follow this chunk till you hit another such point, and then you can again cut a section. So again, this possibility doesn't exist. So this wouldn't even appear in the, eventually, after you are able to get all this Cafarelli's theory, and that I hope we do. Okay, so the motivation is to be as less as possible. Unfortunately, that is so. Singular solutions. So 2-dimension 2D, all solutions are classical, and these are the works of many. Okay, and I'm not very up to date on the historical sort of references. You can say that there are contributions due to Alexandra, where this dichotomy result that Devobrata talked about in dimension 2 was due to Alexandrov, and then essentially I think he had it. Okay, so it's the work of several people. Okay, Alexandrov, Calabi, Kogolarov, and others. Higher D. Okay, so higher means Rn, and bigger than equal to 3. Solutions need not be classical. So Alexandrov solutions need not be classical. I will tell you an example, and this is the example due to Kogolarov. So that will tell you. So Kogolarov, Velos example. So for that you have to exploit this affine invariance property, and you see that dimension 3 higher would step in. So what you do is that you look for solutions u lambda of x prime xn. Okay, so that would be some power of lambda that you adjust, and then u of lambda x prime and xn. So this I have now put it right away. So like I did for the other case with this det of a to the minus 2 by n, so that it sort of balances. Okay, and now what I do is that I compute the determinant, and I want to have that the determinant of u. I start with the example that determinant of u is like 1, and I want this quantity to be also like 1, and that forces what gamma has to be. Okay, so let me okay. So therefore, so when we compute it, this will give me a factor which is lambda gamma n, and from here I will get a quantity which is like in n minus 1, right? N minus 1 and lambda raised to the n minus 1. Okay, so lambda and 2, because twice I derivate, right? 2 times lambda comes in n minus 1 dimension, so it's lambda 2 n minus 1 times the determinant of d square u evaluated at lambda x prime xn. And if I match this quantity, what I get is that gamma has to be 2 of n minus 1 by n, which is equal to 2 minus 2 by n. And therefore, this is reasonable for this kind of an invariance, scaling invariance property of this Monge Ampere, at least for n bigger than equal to 3. But because for n equal to 2, it doesn't mean much, right? So n bigger than equal to 3, what you have is that you look for solutions u of x prime xn equals to mod x prime gamma times h of xn. So now, because of this invariance, and you see that this, because of this invariance property, scaling invariance property, whatever the determinant of this is, it suffices to compute it at 1, 0, 0 and xn. Because in the xn minus 1 direction, it is rotationally invariant, right? And if you compute it, now remember the barrier computations that we had in the fully nonlinear setup. If I do it at 1, 0, 0, 0, 0, so one of the eigenvalues is like gamma times gamma minus 1, u11, and then h, and then there will be like order gamma h, and all the way up to, and so let us see. So this will be u, h, and I. So that will be gamma, and h will be 1, and mod x is like 1. Mod x prime is 1, right? This is the region I'm looking at, right? I'm normalizing it to 1. So all mod x prime disappears. So therefore, this will be gamma, and this will be h prime. And these are all 0. And this will be similarly gamma h prime, because the mixed derivatives have to match. And if you go all the way down, this would simply be h double prime. Now, if you solve this determinant problem, okay, you expand it along this row, and you will find that, okay, so let's do it. Let's do this process. Okay, so this part, if I expand it along here, this I know exactly what it is. It's just the diagonal. Okay, and this diagonal becomes gamma times gamma minus 1, hn minus 1 times h double prime. And for the other one, you see that this is 1. So how much minus 1s I have to take? So minus 1 to the 0. So this will be minus 1 to the n minus 1 gamma of h prime. Okay, and then I go to this matrix. Okay, and then how many rows? So this is the matrix that I need to consider. And now I need to see how many rows do I slide down. So this would be 0, and this is like so this will be another minus 1 to the n minus 2, right? And then the gamma of h to the n minus 2. Oh, sorry, gamma minus n and h to the, yeah, I think this is fine. So, okay, so, but now both of this makes it a minus, because it's 2n minus 3, okay? So therefore, inside what I have is that I can take a part of h n minus 2 out, and then inside what I have is gamma h minus 1. I think it's fine. So gamma h. So wait. So something is. So I forgot the power. Happily ignored the powers of gamma. So this is gamma to the n minus 1. Okay. So gamma to the n minus 1, right? Whatever it is, I don't care. So what inside is like h double prime. Okay. This factor is important, times h minus some function of gamma, some polynomial of gamma times h prime square. Right. So that is the h prime. So gamma h prime. So there is another gamma h prime. I'm sorry. So this is missing. Okay. So because when you do this, I miss this part. So this is what which gave me minus 1 to the n minus 2. But I should have also had this. Once I make this, and it sort of matches everything. Okay. So this is h prime. So this is the nature of the OD. Principally, the nature of the OD that I need to solve. And then you can sort of solve this OD in xn in a small region by Cauchy-Lipschitz theorem or Picard's theorem. Right. You just put the assumption that h of 0 equals to 1. So you want to solve this OD equals to 1. So that you can make the entire determinant 1. Okay? And if you don't care, you just put something like 1 plus xn squared, then in a small enough region, you will have that this is strictly bigger than 0. So if you don't care about the right hand side being 1, you can just put it 1 plus xn squared, but otherwise you can always solve this ODE in a very nice manner to ensure that the right hand side is exactly 1 or whatever the constant that is needed to match this power of gamma. Okay? So you don't solve it for OD equals to 1, you just solve it in a way so that it just matches the right one. Okay. So therefore, what you get is that in that case, you have to put this hn minus 2 inside. Okay, so that there is no h that is lurking outside, because this makes no sense. You put this hn minus 2 inside and you solve the OD, which you can happily do, which is in h double prime. Okay. So therefore, what I get is that I can also, so this is Pogolarov's example. He used the scale invariance in higher dimensions to know that there are solutions like u of x prime xn equals to mod x prime to the gamma, which is 2 over 2 by 2 minus n times h of x prime, such that det of d square u is as smooth is like 1. And this you see is not in C2. C2 regularity phase. And how does this example look? So this example looks is that it curves up more linearly. So there is a tangent plane here. It curves up, but it doesn't curve up like quadratically. It is much steeper than quadratic. So this is more like a picture like this. It's convex, okay? And so, okay. So it is like steeper more than. So this is the xn axis and it curves up in the direction which is x prime. Okay, so this is how the graph looks like. Okay, and now if you see, this is an Alexandrov solution. Why? Because det of d square of u equals to 1 in the region where x prime is not equal to 0, and in the region where x prime is 0, the supporting plane, okay, has to be contained in the directions of the supporting plane has to be contained in along xn, that is along x prime equals to 0, right? Because if you try to curve up, then you cross this graph, right? Here, because the power is more than 1, so you have to cross this graph, because any line that you take which has a positive chunk of xn has to exceed this graph because of the fact that mod x prime is raised to a power which is bigger than 1. So said differently, grad u of x prime equals to 0 is contained in the set where mod x prime equals to 0. So therefore, it is an Alexandrov solution in this region. Okay? And why is the problem? The problem is that to this graph, if I draw it say differently, so suppose I draw this graph differently, well, draw it like this little bit more, and there is a whole zeros along, it is affine on a lower dimensional space. If there is a whole zeros that lies on a line, so if I have to raise a tangent plane that Debabrata talked about, if I try to lift it up, I start seeing the boundary. So the section that is below exceeds the domain that goes to the boundary. Okay, and this is precisely the problem in this example. Now there are examples even worse. You may say that okay, C2 I cannot get, but what about C1 alpha? There is also an example for that. If you take that of d square of u equals to mod of x prime plus mod x prime to the n by 2 times some g of xn, this part you can show, okay, is a solution to a nice equation, okay, outside. But this is the part which is kind of Lipschitz, right? So it is not in C1. And what kind of examples are these? So and for this example that you have, you can show that the gradient is net of d square u is like bounded, okay, bounded from above and below by 1, okay. So it is not smooth, but for smooth you have to do more work. And now for this, how does the graph look? So what you do is that you cut an axis, right, and then you draw this plane, and the whole thing is like bending. So the graph sort of lives in a sort of a very strange way across this, okay? And then the picture is like the same, except for the fact that here you have like a tangent plane now, okay? I'm just exaggerating the picture. Again, the tangent plane at these exceptional points lies in the lower dimension of the space because x prime has lower dimension, okay? At these points, I cannot sort of lift it along the x prime direction. So along this also, you will again have that this is contained in the set x prime equals to 0. Has to be contained in this set, okay? So along these slopes, you cannot lift the graph, okay? So therefore, and in the other region, this solves a nice sort of equation, okay? So therefore, it is again an Alexandrov solution, which is no better than Lipschitz, okay? So what are these problems? So in all these examples that I have, there is a whole line of zeros, right, which exceeds the domain. So and therefore, for the Monge Ampere, it only makes sense to talk about regularity of strictly convex solutions, which have to be defined appropriately. And this is where Luis Cafarelli made some significant breakthroughs in the early 90s. And a good chunk of the theory, I mean, it would not be wrong to say, was that entirely architected by Luis Cafarelli around that period, okay? And we will see some great insights of this theory. So therefore, what I do is that if I have a convex function u, and now I talk of a section, okay, which is to say that I take the supporting plane and I lift it on the graph, okay? So what I do is that I take this tangent plane, so u of y is bigger than equal to u of x plus p dot x, y minus x, which is to say that p lies in this differential of q of x, right? I mean, it could be a coordinate. Then what I do is that I lift this tangent plane up by distance h. Okay? So I look at the section S, H, X, P, which is I look at the set of all y such that u of y is less than u of x plus p y minus x plus h. So let me draw another picture. So there is the plane, and I lift this up by height h, okay? And then this is going to trap a region, right? So if I put it down, this will be the region, right? So this is the height edge, okay? So this is the region where you have that all the function values are such that ui is less than the lifted tangent plane. And now the Cafarelli's theory is about, so let's call it just S of h at x. Cafarelli's theory is about if sh of x is compactly contained in the domain so that the section doesn't go too close to the boundary, then u is regular, strictly convex. Okay, so the theory is as follows. I will just give a description and then I have to go to the proofs of the theorem. So the theory is as follows. So this is my description of strict convexity. That is, to start the process, I need to cut a plane. Okay, I need to cut it by a plane, supporting plane lifted up. And so therefore, in the example of this Minkowski problem, I know that the surface rounds up, so at some point I can cut. So at a point where it's strictly convex, I don't have to do anything. That is, you can lift a section, so everything is sort of round, curved up. And on the other points, then you can do slightly better than just the strictly convex point. You can do it at extremal points. And extremal point, you can again cut a section, right? Because extremal points are characterized by the fact that you can slice it by planes. So there also it will curve up a bit. So the theory applies. And now I say that the solution to the Minkowski problem has to be strictly convex throughout, provided this Gaussian curvature measure is like comparable to, has one density, comparable to one density. Why? Because if I have an exaggerated piece with a triangle, okay, then what I do is that I take any point where it's probably flat, like the one over there, and I follow it till I hit an extremal point. And as I explained, and as they pointed out, that if you slice it by a plane now, here you can apply the theory, and therefore this cannot be flat. This cannot be affine inside. But then there is this whole affine line that joins this extremal point to this, and that cannot happen. So in the very first place, this cannot be flat. So the whole thing has to curve, and once you are strictly convex, what Luis Cafarelli showed is the following. Then everything boils down to the local theory that I will mention. So regularity is that u strictly convex defined in a more weaker sense by the fact that you can cut a section so that the region is compactly contained, strictly convex, and you have the delta of d square u is like f, okay? And f is like bounded, like 1, then u is given alpha. And if u is strictly convex and f is close to 1 in oscillation, that is f is C alpha, then u is in C2 alpha. And once you have C2 alpha, you can keep moving. Okay? Good. And you see that strict convexity necessity because even C1 fails. Oh, I happily erase that example. Where is that example? Oh, there's it is. Okay? And there are other theories which are more recent works. Okay? Sabine, boundary regularity, provided at the boundary values the quadratic separation so that you can slice a section at the boundary, and it's a very deep paper in JAM in 2011. Okay, and then you have De Philippis, Guru de Philippis, okay, Figali and Sabine, who obtained that for strictly convex solutions you have W2 1 plus epsilon estimate. These are very recent, and they apply to, so to speak, quasi-geostrophic equation, which I will not even try to touch because one is that I don't even know, and I wanted Jim to sort of derive this equation, but I think there wasn't enough time there. So it is not even his problem. I kind of told not to. Okay, so this goes in a different direction. Okay, so these are very important estimates even otherwise because this sort of opens the door to further development of Calderon-Zilman theory. Okay, which already is known provided that f is close to 1. So the other theory that you have, the intermediate theory, f is continuous doesn't matter, right? Because every theory is local. Then you d squared u within NP for all. And this uses the fact that f is close to 1, and of course f has to be like 1. This uses the fact that f has small oscillation, because if f has large oscillations, the W2B estimates may fail in general, and there are examples due to Shuji-Awam. So this result of Sabine, De Philippis and Figali just tells you that given a f, there exists a epsilon such that u d square u is in W2 1 plus epsilon, and this epsilon will be depending on this f. So generically, this epsilon has to go to 0 for any given f. There is something that you have, and if you don't assume strict convexity, and by the way, and the other thing is that this is sharp. You need strict convexity even for this, and I cannot tell you this because this is a very recent deep example due to Cornel Monge in his thesis. That if you remove strict convexity, even this estimate fails. Okay. So this is kind of quite good, but I think it's deeper than the example that I just than all the examples that I mentioned. Okay. So this is one, but here established in the same work that if you don't assume strict convexity, you cannot get to 1 plus epsilon, but you can get L1 log. Okay, so that is not only so this to a power which is like d squared u log of d squared u is kind of integrated. Okay, so you can do 1 better than epsilon. Okay, and this is only relevant when d squared u is bigger than 1, right? Okay, so this is some improvement, and maybe the log comes with the power. I have to check. Okay, I don't know. Huh?
DTU is in LP
for all p. If f is continuous. That is it just roughly. So all you need is that f is a small oscillation near 1. So for every epsilon bigger than, so given me there exists an epsilon bigger than 0, such that if f minus 1 is less than epsilon, then u is in W2p. And that epsilon depends on p. That is the theory. So in particular, if f is continuous, you can rescale and you can get as close to where you want. But again, all this theory assumes strict convexity. Okay. And what I said earlier, alluded earlier, is that in 2D, strict convexity always happens. Okay. So and for that I will give an argument of Luis Cafarelli, and that will be postponed to the last lecture. Okay. So now the first more primitive question is that how do you solve the problem? So classical solvability. Solvability. Okay. And this is so this was done around 1980s by Cafarelli, Nirenberg, and Strauss. This is the one that I will describe, and independently by Krylov. And also there are some partial results by Lyons. And it is not smooth up to the boundary, but C2 inside and continuous up to the boundary. And later on, Rudinger and Wang improved, generalized this to more general Hessian equations. Okay, and that is there. A good account of that you can find it in the book of Gilbert and Rudinger, except for the fact that that proof is not true to this Cafarelli, Nirenberg, and Strauss. So I will describe this. And also, so the theorem is as follows. And so what I'll do is that for the time that I have, I'll try to give a detailed proof in the case where you have 0 boundary values. Okay. And then if at all there is time, I will try to point out the differences in the end. But the heart of the matter is in the 0 boundary values. Okay. So what you have is the following. So I will solve the problem. Omega is in C4 alpha. Okay. And I want to say that there exists a classical C4 alpha closure solution to set of d square u equals to f when f is in C2 alpha omega closure and u equals to 0. And not only this, you have uniform convexity, that is the principal curvature are bounded from above and below. That is from the tangent plane, the surface has to strictly curve up, okay, on del omega. And this has a classical solution, okay. And you can then replace it by the right hand side, but then you just need to add an extra sort of a compensating term, which is like an affine function, but in the graph coordinates in the x-end. Okay, and then when you push it, you are able to generate the convexity that you need to compensate for the non-zero boundary values. So I will not even say what after that because I have to end my lecture in 12:45. Okay, so it is a deep theory, and I just don't know. I mean, how to sort of tell you in a more convenient manner. So what is it that I need to do? I know that because that of or the log of the determinant is concave on the cone of positive matrices. Therefore, I know that this as a fully nonlinear operator has a concave structure. So therefore, if I know that UEE is modally like super solutions, subsolutions. Any pure second derivative is modally like subsolutions modulo the fact that there is a right hand side, okay, which I need to take account of. So what is the strategy to solve the problem? The strategy to solve the problem is that you know how to solve it. So given a uniformly convex domain, okay, so what I do is that near the boundary, I take the distance function, so minus of d is convex, okay, because the distance is like sine distance inside, okay, minus of d is convex, okay, and then along the normal I need to add, so this will only have tangential curvatures, and then I need to add plus d square. So therefore, along the boundary, I have that near the boundary, I have a region where that of d square u is bounded from above and below for this. And then I can sort of, I take all, so then I generate the boundary values here, maybe a little bit inside, and then I continue it inside by the convex envelope, which I then mollify. So what I'm trying to say is that in essence, I can extend it in a uniformly convex way all the way into it inside. The key part is to do it at the boundary. Of course, this is not a convex domain. So domain like this, okay? And let me sort of give you a little bit more details because you would not even be realizing why minus d is the one that works. Okay, so let me just tell you a little bit on this. So any graph in the principal coordinate system, you can write it as x prime, phi of x prime, okay? Such that, and this is the 0. We want to find out the principal curvature at 0, such that phi x prime of 0 equals to 0. So that the tangent plane is equal to xn equals to 0, right? So let me draw a better picture. Okay, so there are different directions, okay? And this is the tangent plane. And it's a uniformly convex domain, so I don't really need to care about that. Okay, so now let's look at the region which is the region of increasing normal. So the thing is that if you look at xn minus phi x prime, this increases in this direction, right? So, and this is the direction of inward normal. So, and what is the gradient of this? The gradient of this would be the direction of inward normal. And the gradient of this is simply minus phi xi, or I will just write it simply minus x prime phi and xn, which is 1, right? Okay. And so this is the direction of the inward normal. So the outward normal has the opposite direction. Okay. And this is in the direction of the inward normal. So let me just. So the normalized normal would just be minus x prime phi of square root of wait. Something that confuses me is that so this is my inward normal into the domain, and that is the inward normal is the direction of the okay. So this is so therefore this is the direction of the inward normal, which is the direction of the distance function, right? I know that for the distance function, grad of d equals to this mu, which is the inward normal. So therefore, minus d would exactly, or minus of grad d would be like, which is the outward normal, would exactly be phi of x prime phi 1 plus of minus 1. Okay. So along the principal directions at 0, which is only in the x prime direction, I know that phi is a strictly convex function, uniformly convex function. So the derivative of the further derivative of this, d square of this, should be d square of phi, right? At least at the point where phi x prime is 0, which is at 0. So therefore, d square of d, so d square of minus b is like kappa 1, the principal curvatures, n minus 1, and then 0. But therefore, in order to balance it more, along the normal, I need to put a quadratic term, and that makes it like 2. So minus d plus d square, this could only live in the normal direction. So there morally it is 2. So therefore, I know that for this function that I have hooked up, where I have sort of extended it uniformly convex inside, let's call this function, I have to give it a name, right? So let's call it psi. Okay. So I know that there exists psi, and near the boundary is 0, right? In the case of a ball, it's very explicit. Okay, I just leave it to you. Okay. So it is in the case of ball, it is just 1 over mod x squared minus 1, and it's exactly minus d plus d square all the way up to the inside. But in general, because I cannot do it, I move a little bit inside, and then I extend it by the convex envelope, which I then smoothen it, make it more strictly convex by but wherever there is sort of degenerate convexity, add some little balls, okay, and then I can sort of do it in a very sort of a nice fashion. With whatever it is, then I get that det of d square of psi is equal to some f, which is bounded from above and below. So there is some f from, okay, thus that psi equals to 0 on the boundary. And now what I want to do is that what is my problem? So let me erase it for now. My problem is to solve it for general det of d square u equals to f. So because I want to solve the solution in C4 alpha closure, so then I have a Banach space which is C4 alpha, and I have another Banach space which is C2 alpha. You fill in the details as to what I mean, okay? And this is say y. And I want to go from this to this. Okay, and I know that there is one place where I can solve it. And then what I do? I run a straight line homotopy. So I take all T of F naught, the T of F naught plus 1 minus T of F, and I look for all such T's where I can solve. When T equals to wait. So 1 minus T of F naught, this is better, okay, plus T of F, okay. So I can solve it for T equals to 0 because I have an explicit solution. And then I want to see whether how far I can move, okay. So now look at the set of T's. So let's call it A. The set of T's where you can solve. And I want to show that this is both closed and open. Open is soft. That is just the classical elliptic theory for which the derivative will come into play. So what is it to say that? That is the same as saying that at a T that I can solve, that of d square of u minus this T, let's call it f of T, as a solution, right? Suppose I have a certain T, I'm able to move at certain T, and then I want to see whether I can extend this homotopy, this solution class, even for more T to the right, okay? So then what you do is that you compute the differential along this, right? You apply the implicit function theorem. When you compute the differential along this gives you, as I said, so when you do this, this gives you det of d square u, okay, at a T naught. Suppose you want to see, so fix a T naught. So suppose at a T naught as a solution, whether you want to see that from that T naught, whether you can move. At least there is one T naught, which is H naught, where you have an explicit solution. So what you do is that you take det of d square u, and then the inside is just the trace of d square of u inverse of this. So this is the Fresher differential, right? So this is of g of u of t, and this is simply dgu, whatever you call it. Okay, this is the Fresher differential, and you want to show that whether it exhausts whether it's a surjective mapping, so that the inverse function theorem can be applied. So that is, you have to solve it for this. You have to solve for u in the space which is its own tangent space. It's a function space, Banach space, linear space. Okay. And you have to solve it for this equals to, let's call it V. You want to find the V in X, which is its own tangent space. It's a non-linear space. Vij, or I should call it square of V equals to a G that I'm interested in Y. But then what can I say? This value is f of T naught. I move it to the other side. This is nothing but trace of d square u minus d square v equals to G by F T naught. And with boundary values, T equals to 0 on the boundary. By this product theory, I can always solve this. Okay. So elliptic theory is important. So one cannot learn the optimal transport without barring all of PDE. Okay. So this is one. So therefore, that means what? This T naught can be continued, right? So therefore, I can solve for T naught plus some delta. So T naught to T naught plus delta by the implicit function theorem, I can solve it a little bit more. But then the hard part is to show that this is a closed set. Closed set means that I have to get uniform C4 alpha estimates for this PD all the way up to the boundary. Till this part is the soft part, where the linear series, of course, I mean, it's a development over a long period of time, over the last, like from the 1950s to 70s or so. But at least, I mean, that for our question of interest is still classical. So the hard part, which is the new thing that these Cafarelli, Nirenberg, and Sprague, and also independently Krylov brought in, was to get uniform C4 alpha estimates for these problems. If you get estimates, then you can show that the set of T's are also closed, right? Because then you can get a set of Tn which goes to some T, and for all these you have stable C4 alpha estimates, so therefore you can pass to the limit, and when you pass to this limit, you solve the limiting problem, right? So the main thing reduces to knowing the uniform C4 alpha estimates, and based on and let me tell you that this is now good enough to know just the C2 estimates, because I said for Monge Ampere, if you know that d square u is bounded from above, then you are more or less done. So let me sort of justify it over here. So I will do it by the log. So log of the determinant, okay? Of u, suppose this log of f, and u is 0, okay? So then what I do is that I differentiate it, okay? I differentiate it, so let u be, so let d square u inverse, I represent it as u, okay? So when I differentiate it, 1 by det u, then det u comes out, so they happily cancel one another. So the linearized one is equal to uij of ueij equals to log fe, right? Yes, so log fe. f is bounded from above and below because log f is also good, right? And in the right space. And then what you do is that you differentiate it again. When you differentiate it again, what you get is that you get uij, ueeij plus something which is, and we know that this log is determinant is concave, so what you get will be a quadratic form, right? You will get a quadratic form, a non-negative quadratic form because of the concavity, which I will explicitly compute at a later point when I in my third lecture, but at least I know that it's concave. So if you derivate it twice, you have to derivate this uij again. When you derivate,
bigger equal to non-negative or not positive?
sorry, this is less than equal to 0. Sorry. Quadratic form which is non-positive.
Minus of it, you have to differentiate the inverse, right?
Yeah. So here I have, okay, if you want me to differentiate the inverse, so here is the inverse. So what I have to do is that I have to compute a plus epsilon inverse, right? At epsilon equals to 0, right? And this is just like this. I will use a plus epsilon inverse times a plus epsilon b equals to 1 and identify. Okay, and then you derivate. Okay, the first derivative that you get at epsilon equals to 0 will be exactly this which we want to know. Multiplied
is less or equals to 0, not bigger equals to 0, right? The
no, this quantity is less than equal to 0.
Right, that is what. That is what.
So I can compute it explicitly this quadratic form, which is less than equal to 0,
Right.
which I need for my last lecture,
Right.
but not for this lecture. So can I skip this computation?
Yeah.
So all in all, so anyway, so since I started, let me just finish it. So I'll just move this to the other side, okay? And plus what you have is the epsilon of b. So that will simply be a plus epsilon b inverse of b, and this will be equal to 0. And therefore, when you put epsilon equals to 0 in all of that, what you see is that this limit as epsilon equals to 0 will be the Jacobian, and this is equal to minus of a inverse b of a. Because you move it to the other side, this becomes minus a inverse at epsilon equals to 0. You put epsilon equals to 0 because you have derivated d by d epsilon of epsilon b. You both move there. This becomes minus a inverse b, and then a is there, so this becomes a inverse. Okay, so when you put everything here, this simply becomes so whatever it does. Okay, so this becomes, so I have to compute minus this, so this is u of il, and then you will have u of elj, and anyhow, so this is the thing that I have to bring. Okay, so this is less than equal to 0 because the quadratic form is less than equal to 0, and this is the right hand side. So all in all, what I'm trying to say is that if you remove this computation, so this I would have written it down, but I will do it at the very end. Okay, so less than equal to this. So therefore, it's a bigger than equal to minus of log FPE. This is what I need to use. Okay, so this is less than equal to 0. To compensate this, this has to be at least sufficiently big. So that means that if I denote this operator L as trace of d square to inverse dot L, okay, then I have that L of UEE is bigger than equal to a minus constant. Okay, and now on the other hand, I know that because d square u inverse is the inverse of d square u, so I know that u of uij equals to n. Right? So that means that L of u equals to n. So this I erase. So L of u equals to n. So if I sort of put it, so therefore what I have is that I can add this term, okay? So if I have UEE plus large K of u, which balances this C, then I have that for this B, L of B is bigger than equal to 0. And this B is, and so therefore, supremum of B in the inside is less than equal to the supremum of B on the boundary. In the case when it was 1, I don't have to worry. But because I have an F, I need this extra compensation by this U. Okay, this is just to show you that this theory extends. And therefore, when you do this, when you plug in this, this is simply UEE plus U, right? And now let me tell you how to bound this U. So therefore, UEE at the boundary, UEE in the inside will be less than equal to UEE at the boundary plus max of some constant times max of U in the whole domain, right? And for because it's a U is a convex function, bounding the max inside is the same as the bounding the max on the boundary, right? The norm of this max, okay? Because the boundary values are all 0, so the max of mod of U is only realized at the boundary. But this is not very difficult to do, because suppose this is my solution, and I know that delta of d square u equals to f, and I have that model one f naught. So what I do is that I take a small multiple, so I take a small c of psi naught, which is above, and I take a large multiple of psi naught, which is below. So what I do is I perturb this psi by two sides. One c so that the curvature is above. The maximum principle tells you that this graph has to be below. Okay, and the other large psi so that the curvatures are too large. Then the maximum principle will tell me that large c times psi is strictly below. So this is my u, this is my little c times psi, and this is my capital C times psi. So with this, not only do I get a bound for u, so the max of u is controlled. So therefore, in order to control the max of u at the inside, max of the second derivative in the inside, I just need to control it at the boundary, right? Because k of u is controlled. But from this, I have interesting inferences. Not only am I able to control u between these two paraboloids. It's not exactly a paraboloid, but it's like something which is close to a paraboloid. As soon as you get near the boundary, if you start looking into the distance coordinates, and I also end up controlling the normal derivative, because the normal derivative, which will be positive, is controlled trapped by the normal derivative from below of this guy, and the normal derivative, the normal derivative from outside will be trapped by from below by the normal derivative of the top, because it has to rise up less, and the normal derivative of the bottom. Okay. So therefore, what I have is that the normal derivative is not only positive because the function is kind of increasing across, but it is trapped between these two, and this has larger slope. So u mu is less than equal to constant times sin mu at the boundary and bigger than equal to little sin mu at the boundary. So u mu is bounded from below by a positive constant. Important. And now the thing is that the tangential derivatives are anyway bounded because it's zero, so there is nothing to bound. And therefore, if I know how to control UE at the boundary, I would know how to control UE in the inside. Okay, so I just need to control UE at the boundary. So this is the next part of my work. Okay. So which is what I what do I do? So first let's control all the tangential derivatives at the boundary. Even though U is zero, but the whole surface curves off, right? So therefore, the second you see, like, so you will take into account the second order curvatures which are strictly positive. So let's do this computation. So I am just looking at a point where in the principal coordinates where you have that phi of x prime, phi of x prime. So I'm just looking at this point where you have the principal coordinates, the tangent plane is xn equals to 0. I just found u of xi at this point. And if I do it uniformly at every point from above, then I would know, because it has to satisfy the Monge Ampere. Qualitatively, it is C4 alpha up to the closure. So therefore, all the data of d square is bounded from below. And then the Evans-Krylov theory will take over up to the boundary, will tell you that U is uniformly C4 alpha inside. That is the theory that I have already developed, starting from my first lecture in a flash. Okay. So first let me control all the softer part, UXC, but this is the important part. I'll tell you why. So I take some xi, which is in 1 to n minus 1. And the normal is what? So this is xn. And so the normal is minus xn. Okay. And so u of minus n I know is positive. So u of minus n, so minus un I know is positive, right? Because this is the direction of the outward normal. Good. So now let's implicitly differentiate the same that we did in free boundary problems. Okay. So you have that u of x prime, phi of x prime equals to 0. So you derivate it once. So you get that ui means u of xi plus un phi I equals to 0. Derivated it once more. So you get that uii, okay, plus uin phi I plus un phi ii equals to 0. But at the point 0, this quantity vanishes. At 0, I get that uii equals to minus un times phi ii. But this is bounded by the, because I am in the principal coordinate system, this is bounded by the principal curvature along the xi axis when I rotate my tangent plane to the principal directions. Okay. So therefore, I get that uii is bounded from below by minus un, which is a constant, times c times kappa I. Great. So I get bounds on all the tangential second derivatives from below by a positive constant. This is going to help me. So I get, so therefore, step 1 is accomplished, step or maybe several steps have been done already. Okay, so step 1 that I will summarize is that I have bound u, I have bound grad u, and I have bound this xi from below. And it also gives a bound from above, right? Clear? Because it's positive because all these UNs are trapped between, you use this estimate, okay? And the fact that these curvatures cannot be too large, okay? Because it's uniformly convex, so the curvature doesn't change all across. It's a compact domain, right? So it cannot change too much. So great. So now the thing is that, so this also gives you a bound from UIN from above, okay? In a similar way, by using this estimate instead. So it's like UII is roughly comparable to 1 modulo the principal curvature, okay? So I get this estimate. So good. So now what is the next? So let me write d square x prime of u, and that is exactly equal to minus un of 0 to the 0 times this kappa 1 up to kappa n minus 1. Good. So this is done. And now I want to bound uxi xn. So that is I want to bound uin. So what I do is that let me not write I because I use it in the operator also. I want to bound some uln, where n is in 1 to n minus 1. Okay. So I want to come. So now for this is where the boundary first the barrier and the boundary Harnack inequality comes into play. Okay. So the barrier and the boundary Harnack inequality comes into play, where you need to find a quantity that vanishes sufficiently at the boundary. So let's write it out. So what I know is that from this implicit differentiation, okay, from this one, I know that ui equals to minus un times phi I, okay, minus ui times phi un times phi I, and so this essentially behaves like c of some kappa I times xi, c of kappa times xi times un, right? So this behaves like, or I will keep the un as it is. So this is, in fact, I mean, I better do. So it's kappa I un xi plus the second order square terms, right? Because phi is 0, 0, the curvature changes exactly in this way. So the phi I, they grow like the principal curvature in the direction of xi, and then order xi square. Okay. So this is how the phi I behave, right? Order xi square. Okay. So this is quadratic. But the problem is that, so therefore the right quantity to consider is to trap a barrier is to consider ui plus kappa I un xi. Well, I want to put ul because I want to feed everything in the, this is kappa I, okay? I don't want to match with I because I need to apply that operator, the linearized operator, and that will kill me. Then I have to find some other LM, and that I don't want to miss. Okay, clear? It is not like I'm doing something very deep over here. I'm just sort of cooking up notations for my own computational convenience because I really don't know what I'm doing. So XL of UN. This is not a good equation, but you see that this is a part of an angular derivative. This is the another great insight that this Cafarelli-Nirenberg-Sprague had. So the idea is not to play down any part of this theory. Okay, I'm doing it first doesn't mean that you see, like I just find everything so trivial. It's just that I just have to do it fast for the time constraints that we have. So do appreciate that these are deep parts of the theory. Now instead, what I do is that I apply to the angular derivative, right? So the angular derivative, so let's call it theta L, which is in the direction of EL and EN. That essentially looks like, this is a part of it. It looks like xn UL minus xn UN, right? So at least one part of it is there. Okay. So therefore, in order to complete it, I better make it XL UN. So I would look at this quantity. So it's not UI, it's UL minus XN UL. Because this is exactly U theta L. And this is an invariant direction for which I can do the same computation. So I know that if my L was the trace of d square U minus, then L of U theta L ij, okay, L of U theta ij is equal to log of f theta L, and that is bounded, right? Right, that is bounded from above and below. Clear? Clear? Because you just take this theta L, and this is essentially this part. And now comes the next part is to know that what is the right barrier to compare it with. Okay, so this I will call as my WL. And this satisfies, so therefore, L of WL is also bounded because this part is bounded and L of UL is already bounded by log of. So L of WL is bounded by this C and another C, which is bounded by log of FL, which is like another C, right? In absolute value. Clear? The log of the quantity on the right. Great. So now how do, at this point is where I use the fact that my surface serves up a log. Okay. So here is my surface. Let me exaggerate it even more. So whenever you have to convince, you have to draw a picture that almost convinces you, even if it is deceptive. The idea is to make it as less deceptive as possible. Okay. So my surface is very largely uniformly convex. Okay. Except that it doesn't contain all the way up to infinity. Sort of at some point closes. So now here is the thing. So this is my principal coordinates, and I know that this is x prime, phi of x prime, and I know that around this xn is at least a good chunk of x prime square up to this, right? Why? Because the surface has to curve up. Clear? And because finally it closes, okay, I would know that if I go far up in the direction of xn, after this, I can just use the fact that xn is bigger than equal to some delta to find a large k. So in this region, so therefore I can always, there exists a k which depends on how the support of this uniformly convex domain says that k times xn is bigger than equal to a constant times mod x square, which even includes xn square. Because near this region, xn is going to dominate over xn square, and xn is going to dominate over x prime square by uniform convexity. And little bit away, even though I know that xn square will dominate, but since xn cannot lie in an infinite region, it is trapped somewhere, I can cook up a big constant to say that k of xn is bigger than equal to c mod x square. Good. So now let me first bound this. So this is an information to you, and this is what I will use to bell bars, so to bound it in a most sort of a judicious way. So I will bound this WL near the boundary. Okay. So mod of WL is less than equal to UL, and I will plug the first quantity, which is kappa L, UN, XL, and then I will isolate the rest quantity, which is XN times kappa L, XN times what is it called? UL. So these are already bounded because these are the first derivatives. And this part I know grows like what? This part grows like c times mod x square, right? It even grows less than c times mod x square, like x prime square. But okay, I will put x square. Okay, just a larger quantity. And then this part grows like this. Curvatures are strictly bounded from below. Okay, but in this case I use the bound from above, and this is bounded by c times xn. So the whole domain lies on the positive part, so I don't need to take mod of xn. Okay, and now here is the trick that I do. I write it as c times, I take a large c, a large a, that I make it negative. Okay, so I make it like c minus a mod x square. But in order to compensate the negativity, I need to add plus k of a xn. So this balances out, and then there is a cxn. And you will see why, because this is what will put me the barrier from the other side. Okay. So what I have is that, so therefore this is less than equal to WL is less than equal to k of a xn, sorry, kc plus k of a xn. But the important thing is to bound the curvatures minus c minus a mod x square. Okay, so therefore if I now take a new function g, which is equal to a minus c mod x square minus this c plus ka xn, and then this plus minus wl, I know that this g is less than equal to 0 because this is bounded in absolute mod by these quantities, and I have inverted this quantity. Okay, and not only that, you know that g of 0 is equal to 0. You just put in 0. Okay, this is another information, and now I need to know that n of g is good. So n of g is modally like this part, right? This is like A minus C of summation of UII, XII, which is exactly this, and then minus L of WL plus minus L of WL, which is bounded. But then summation UII is good because it is the trace of the matrix inverse, which is controlled by, which is bounded from below by the product up to the right power. But the product is the determinant, and I know that determinant means the F inverse, but if F is bounded below, F inverse is bounded above. Okay, so therefore this trace is bounded below, and if I take A to be large, I can sort of kill the effect of this. So if I take this A to be large, I can ensure that this L of G is strictly bigger than equal to 0, G of 0 equals to 0, and G on the boundary is less than equal to 0. Right? This just tells you because these are all boundary estimates. G of 0 and G is less than equal to 0 on the boundary. Now, what does it say? So G is negative 0, so that means that G of n, G of the normal is strictly bigger than 0, right? So therefore G of n or bigger than equal to 0, that means that G of n is less than 0. If G of n is less than equal to 0, that is just simply telling you that minus C plus A. So therefore this simply says that minus of C plus A xn n plus the W alpha n plus minus W alpha n is less than equal to 0. Okay? Clear? But W alpha n at 0 is exactly equal to ULN at 0. Because if you look at the definition of W alpha n, because if you put Xi and Xn equal to 0, Xn and Xn equals to 0 at 0, this is the only thing that survives. And this gives you a bound on ULN. Because you can take plus minus, you take it to the other side, you take it to the other side, you get that ULN at 0 is less than equal to C plus AA. And how is this A chosen? A is chosen large enough so that this, the corresponding contribution that is coming for the linearized operator for this is dominating this L of WL that is already controlled. Good. So this is there. So this gives me the control. And this is not only the control because I can take plus minus, so it's a control in the modulus. So this is how the structure looks like. And now I can compute UNN by the equation. Okay. So, but then you have to realize a certain algebra. So here is my matrix. Here is d square x prime of u. Okay. And here is UNN. And here is all these ULNs. So therefore, what I get is that det of d square x prime of UNN is some polynomial that involves all the other derivatives, which is d square of not UNN, but either ULN or ULL, okay, and all the other ULJs, except for the fact that both of them are else, right? Because this UNN is isolated. And now I use the positivity of this matrix. If I use the positivity of this matrix, I can put it below because this. So anyway, so det of this is this plus this equals to something quantity which is S, right? I'm sorry. So this is the total determinant of this. This, just think of it as 2 cross 2, which is the easiest thing to do when the time is up. This times this, and then all the other cross terms which are over this. Then all the other cross terms which excludes this, okay? This is covered. All the other cross terms are only over there. So you move, this is a polynomial over those which have already been bounded, and the right hand side which has already been bounded. So what you get is that in effect, det of d square x prime of u n minus 1 cross determinant times u of n equals to is bounded by a right hand side which is bounded, okay? Because and therefore UNN is also bounded because this is bounded from below. So therefore, by using the equation, I am able to bound all the UNN derivatives, okay? And therefore d square u is bounded at the boundary. And then by the boundary Harnack near the boundary, you can get C2 alpha, and then you can upgrade it to C4 alpha, right? One at a time. Because once you cross C2, then you can keep bootstrapping using the theory. The key thing, as I said, this is at least this is the fulfillment of the first part of my strategy that I enunciated in my first lecture, that the typical machinery in place is that, or the typical idea that you sort of begin with is to show that d square u is bounded from one side. And then by the Monge Ampere conditions, you can bound in the other direction as well, which grants the operator the uniform electricity, and some modification of the det is log log or the det of 1 by n is a concave operator, then the Evans-Krylov and the Schroeder theory gives you whatever regularity that the domain and the source has. Okay, so this finishes the proof of Siena in the case when the boundary values are 0. In the case when the boundary values are not 0, you have to sort of ensure that minus un is sufficiently positive. So you take u minus kxn. Okay, for a large k that matches the principal curvatures of these phi i's or the second derivatives of this phi i's, and then also how the third order perturbations will behave. So C3 from that approach, because you also care about because if you remember, I did the expansion of phi I as kappa I as xi plus the second order part, but this is like the third order part of phi, right? Third order part of phi. So therefore, you have to take this k, which also takes into account that, and then there is a comparison principle also which is in play. So it is not entirely trivial. So let me just not push it aside, but it can be done. Okay. So real big deal in this theory is to understand the zero case. Okay. So therefore, at least from this analysis, you see that if you have C3, at least there is a hope that you can do this theory. So the original Cafarelli-Nirenberg's plug theory was for C4 alpha, and then it was improved to C3 by Wang, okay, and then Wang in that paper or the later paper he showed that C3 is the sharp regularity that you can have. So if you go to C21, the solutions need not even be C2 up to the boundary. Okay, so the boundary solvability is also an issue. So Monge Ampere solvability is also a research area where people work on in different situations and so on. But this really doesn't. If you look at this proof, except for very little, it doesn't really exploit the precise structure of the Monge Ampere operator, okay? Which the last lecture, which I hope is not a nightmare for me, but if we are able to successfully do, we'll get the interior regularity.
Can you explain a little bit more about why did you subtract? I mean, why subtracting that thing is the?
Why am I subtracting that thing?
Yeah, is the right choice.
Because the thing is that when you do this implicit differentiation, assume that the tangential derivatives of g are 0. Okay, then you still get a term which is like minus of, so if I do u of u minus g, say xi, okay, u minus g matches at the boundary, right? So this is derivative 0. This would then be minus of u minus g xn of what is it called? The d square of, agreed? When I do xi, this is what I will get if I apply everything to u minus g and do the same implicit differentiation.
Not for the boundary. So you mentioned that after.
Oh, that inside.
Yeah.
Oh, inside. Oh, I see. You mean un minus kappa xi, that one. Oh, because this is the part that decay. So this is I think, what was it? I forgot. So this is ul equals to kappa I xi plus the other thing, right? So what was so what was it? I've forgotten now. So that is okay. So uxl minus. So let me see where is it written? Have I erased it?
Yeah.
So this one.
Right.
So ul plus kappa l un xl. You need this term to have quadratic growth. So that you can use a barrier of this type, a quadratic type, to make the Monge Ampere like 1 or the linearized operator like 1.
Quadratic needed for the determinate.
No, for the linearized operator.
Linearized
Which
operator.
is essentially the same, because I know that for the det of d square u is like 1.
Yeah.
So therefore, det of d square u inverse is also like 1. So the trace of the inverse is also sufficiently positive.
So quadratic needed because of the determinant is.
Okay. So this is how you sort of run the theory, and then